Welcome everyone. I'm excited to kick off today's presentation. Today we'll be exploring the fascinating topic of electric current and its effect. On this first slide, you'll see the title and subtitle, setting the stage for what's to come. Over the course of this presentation, we'll look into how electric current works, its various effects, and why it's so important in our daily lives. Let's dive in and discover more together. Let's take a quick look at what we'll cover in this presentation. First, we'll start with the basics of an electric circuit, which is the foundation of how electricity works. Then, we'll explore different electric components, the building blocks of any electrical system. Moving on, we'll look at electric symbols, which are essential for understanding circuit diagrams. Next, we'll discuss electric appliances and how they fit into our daily lives, including their efficiency and how we can make them safer. We'll also cover heating elements and the heating effects of electric current, which are important for appliances like toasters and heaters. Then, we'll delve into the magnetic effects of electricity, leading us to electromagnets and their applications. We'll also examine household safety devices that help protect us from electrical hazards. Lastly, we'll look at electric bells, a simple but classic example of electromagnetic devices. Throughout this presentation, you'll see how all these topics connect to give us a comprehensive understanding of electricity and its role in our everyday lives. Let's talk about what an electric circuit actually is. Essentially, an electric circuit is a path through which electric current flows. This path starts from a source, like a battery or a power supply, and then travels across various components such as resistors, switches, and bulbs. The key idea here is that the current needs a continuous loop to keep flowing. Without a complete circuit, electricity can't move and devices won't work. Understanding this flow is fundamental because it helps us see how electrical devices operate and how we can design circuits to control that flow. Throughout this presentation, we'll see how different circuit components work together. But at the core, it's all about creating that proper path for current to travel efficiently. Let's take a closer look at this diagram. As you can see, an electric circuit diagram is essentially a visual representation of an actual electric circuit. It uses symbols to depict various electrical components and lines to show how they are connected. This makes it much easier to understand and analyze the circuit without having to deal with the physical setup. The key point here is that these diagrams are not random. They follow standard symbols and conventions, which help everyone interpret them consistently. Whether you're troubleshooting, designing, or studying circuits, a clear diagram like this is an invaluable tool. Connecting this to our overall theme, understanding circuit diagrams is fundamental because they serve as the blueprint for building and diagnosing electrical systems. They simplify complex arrangements into understandable visuals, enabling us to work efficiently and accurately in the field. Now, let's talk about electric components. These are the various parts or elements that we use to make an electric circuit. Essentially, whenever you're building a circuit, you're combining different components to create a functioning system. These parts can include things like resistors, capacitors, switches, and batteries. Each component has a specific role, and together they work to control, direct, and power the electrical flow. Remember, understanding these components is fundamental because they are the building blocks of any electrical device or system. By knowing what each part does, we can better grasp how circuits function as a whole and how to troubleshoot or design new ones efficiently. So, these components are at the core of everything we're going to explore in this presentation. Let's look at some examples to better understand the concepts. When we talk about a simple electrical setup, we often include components like a cell, a battery, connecting wires, a bulb, and a switch. The battery is actually made up of two or more cells connected together to power the circuit. The switch is used to control the flow of electricity, turning the circuit on or off. The wires connect all these components, allowing current to flow from the battery to the bulb, lighting it up. Recognizing these examples helps us see how basic components work together to create a functioning electrical circuit, which is fundamental to understanding how electrical devices operate. Let's talk about electric symbols. When we look at circuit diagrams, it can be quite cumbersome to draw or interpret every actual component in detail. So instead, we use specific symbols to represent those components. These are what we call electric symbols. They serve as a shorthand, making diagrams clearer and easier to understand. Recognizing these symbols is essential because they help us quickly identify parts like resistors, capacitors, switches, and more. By using standard symbols, we ensure everyone understands the diagram the same way, regardless of language or background. This is a key part of the overall theme of understanding and designing electrical circuits efficiently and accurately. Now, let's look at the heating effects of electric current. You might have noticed that many everyday appliances generate heat during their operation. For example, water heaters, also known as geysers, electric irons, room heaters, and similar devices. These are all examples where electric energy is converted into heat energy. This process is what we call the heating effects of electric current. Essentially, when electric current flows through a conductor, part of the electrical energy is transformed into heat. This is a very important concept because it explains how these appliances work and why they produce heat. Understanding this helps us see the connection between electricity and heat, and how we can harness this effect for practical uses in our daily lives. Now, let's move on to the section about electric appliances. These devices are an integral part of our daily lives, making tasks easier and more efficient. When we talk about electric appliances, we're referring to a wide range of devices, from small gadgets like toasters and coffee makers to larger appliances like refrigerators and washing machines. One key point to remember is that these appliances rely on electricity to operate, which means they can significantly impact our energy consumption. That's why energy efficiency is such an important consideration when choosing appliances. Additionally, understanding how these appliances contribute to overall energy use ties back to our theme of sustainable living. By selecting energy-efficient models and using appliances wisely, we can reduce our environmental footprint and save on energy costs. So, in essence, electric appliances are not just about convenience. They also play a role in our broader efforts toward energy conservation and sustainable living. Let's talk about heating elements. So, a heating element is basically any appliance that produces heat when electricity flows through it. The core principle here is that heat is generated when electricity passes through a wire. This wire or coil of wire is what we call the heating element, or simply the heating element. Understanding this is fundamental because it explains how many common appliances like toasters, electric stoves, and even electric heaters work. The key idea is that the electrical energy gets converted into heat energy through resistance in the wire. So, whenever you see a device that heats up, you can think of it as containing a heating element doing the work. This concept ties into the overall theme of electrical appliances and how they operate efficiently through proper design of these elements. Let's talk about the factors that influence heat production in a wire. The amount of heat generated actually depends on a few key things: the length of the wire, its thickness, and the material it's made of. Now, good conductors are materials that let electricity pass through them easily, which means less heat is produced. Conversely, if the material is a poor conductor, more heat is generated. This is why heating elements are typically made from materials with low conductivity or high resistance. These materials resist the flow of electricity, causing more heat to be produced, which is exactly what we need in heating devices. So, understanding these factors helps us choose the right materials for specific electrical applications, especially when heat generation is a critical factor. When it comes to materials used for heating elements, two of the most common are tungsten and nichrome. These materials are chosen because of their ability to withstand high temperatures without melting or breaking down. For example, the filament in an incandescent bulb is actually made from tungsten, which is excellent at handling the heat and providing the right amount of resistance. Tungsten is known for its very high melting point, making it ideal for such applications. On the other hand, nichrome is a special alloy made from nickel, iron, and chromium. The combination of these metals gives nichrome its durability and resistance to oxidation at high temperatures. It's also important to note that connecting wires, like those made from copper, are not hot to touch. That's because copper has good electrical conductivity, but doesn't have the same high resistance or ability to withstand heat as tungsten or nichrome. This helps keep the external wires cooler and safer to handle. So, understanding these materials helps us see why certain metals are chosen for specific parts of heating devices, ensuring safety, efficiency, and durability. Let's talk about the efficiency of electrical appliances. When electrical energy is used in these devices, sometimes it gets partly converted into heat energy. This is a common situation, but it also means there's some energy wastage, especially in machines and appliances where that heat isn't actually useful. Now, you might have noticed that many appliances have stars on them. These stars indicate the efficiency or rating of the appliance. Think of it as a way to quickly gauge how well the appliance uses electricity. The more stars an appliance has, the less energy it wastes as heat, meaning it's more efficient. This idea of efficiency ties back to our overall goal of conserving energy and using resources wisely. By choosing appliances with higher star ratings, we're not just saving on electricity bills, but also helping the environment by reducing unnecessary energy wastage. Now, let's talk about household safety devices, specifically the types we commonly use. There are two main types to be familiar with: fuses and MCBs, which stands for miniature circuit breakers. Starting with fuses, these are simple but essential safety devices. They work on the principle of the heating effects of electricity. Essentially, a fuse contains a wire that melts or breaks when a high current passes through it. This action interrupts the circuit, preventing the flow of electricity into devices. The key point here is that fuses protect our appliances and homes by stopping excessive current that could cause damage or even fires. Moving on to MCBs, or miniature circuit breakers, these are also safety devices used in households. Like fuses, MCBs are designed to break the circuit, but they do so automatically in response to overloads. When the current exceeds a safe level, the MCB trips and switches off the circuit. This automatic response helps prevent damage and ensures safety without the need to replace a fuse each time. Overall, both fuses and MCBs play crucial roles in household safety by protecting us and our appliances from electrical overloads. Understanding how they work helps us appreciate the importance of proper electrical safety measures in our homes. Now, let's explore the magnetic effects of electricity. When a conducting wire carries an electric current, it starts to behave like a magnet. This means it can produce a magnetic field around it. You might have seen this in action with a magnetic compass. When the current flows through the wire, the magnetic field influences the needle of the compass, causing it to deflect. This is a direct demonstration of how electricity and magnetism are interconnected. It highlights one of the core principles we're discussing today, that moving electric charges generate magnetic fields. Understanding this relationship is fundamental to many electrical devices and technologies we use every day. Now, let's look at the factors affecting the magnetic effect of an electric current. The first point to remember is that it is directly proportional to the number of turns in the coil. This means that the more turns or loops you have, the stronger the magnetic field will be. Think of it like stacking more layers to increase the magnetic effect. Next, the magnetic effect also depends directly on the amount of current flowing through the coil. So, the higher the current, the greater the magnetic field generated. It's important to see how these two factors, number of turns and current, work together to influence the strength of the magnetic effect. Understanding these factors helps us control and optimize magnetic fields in various electrical devices. So, whenever we're designing electromagnets or motors, adjusting these parameters is key to achieving the desired magnetic strength. Now, let's talk about electromagnets. An electromagnet is essentially a temporary magnet, meaning it only works when electric current flows through it. The key idea here is that a current-carrying wire can behave like a magnet. When electricity flows through the wire, it creates a magnetic field around it. This magnetic field is what makes the wire act like a magnet, but only as long as the current is flowing. Once we turn off the current, the magnetic effect disappears. This concept is really important because it shows how electricity and magnetism are interconnected. Electromagnets are widely used in many devices, from electric motors to scrapyard cranes, because they can be turned on and off easily. So the main takeaway is that by passing current through a wire, we can generate a magnetic field temporarily, which opens up so many practical applications. Now, let's talk about the various uses of magnets and magnetic materials. They are essential in many devices and appliances we encounter daily. For example, motors, generators, and loudspeakers all rely on magnetic principles to function effectively. You'll also find them in hard disks and MRI machines, where they play a crucial role in data storage and medical imaging, respectively. Magnets are also widely used for separating iron materials from junk or scrap, which is incredibly important in recycling and waste management. This process helps in efficiently sorting ferrous materials from other waste. Another fascinating application is magnetic levitation, where objects are suspended without any physical support, thanks to magnetic fields. This technology is used in advanced transportation systems like maglev trains, providing a smooth and fast ride. Finally, magnets are key in magnetizing materials to create permanent magnets, which are used in countless applications, from simple refrigerator magnets to complex industrial machinery. All these uses highlight just how integral magnets are to modern technology and industry, connecting to our broader theme of understanding magnetic properties and their practical importance. Let's take a closer look at the electric bell. Essentially, an electric bell operates on the principle of electromagnetism. When an electric current passes through a coil, it creates a magnetic field. This magnetic field then attracts a metal armature, which strikes a bell to produce sound. The key idea here is that electricity and magnetism are interconnected, and we can use this relationship to create useful devices. This principle is fundamental not only to electric bells, but also to many other electrical appliances. So, understanding electromagnetism helps us grasp how these devices work and how they can be used efficiently in our daily lives. Let's take a closer look at how an electric bell is constructed. It consists of several key components: a curved iron rod mounted on a metallic strip, a switch, a hammer, a gong, and of course, a source of electricity. Now, the connecting wire is wound around the iron rod in such a way that it acts like an electromagnet when current flows through it. This is a crucial point because it's this electromagnetism that drives the operation of the bell. One end of this wire is connected to a contact screw via a switch and the power source. The other end is attached to the lower part of the hammer, which is called an armature. The armature rests on the contact screw and is positioned in front of the metallic gong. When the circuit is completed and current flows, the electromagnet pulls the armature, causing the hammer to strike the gong and produce sound. This simple yet effective design highlights the fundamental principles of electromagnetism that are central to many electrical devices we use daily. When you press the switch to the on position, current starts flowing through the wire. This flow of current turns the iron rod into an electromagnet, which is a key concept because it demonstrates how electricity can generate magnetism. The electromagnet then attracts the armature, which is a movable part in the device. As the armature moves towards the gong, it strikes the gong and produces a sound, serving as an audible signal or alert. Now, here's the interesting part. When the armature moves and hits the gong, it also causes the connection between the armature and the contact screw to break. This break in the circuit is crucial because it stops the current from flowing through the electromagnet, causing the iron rod to lose its magnetism. Without the magnetic field, the armature is no longer attracted and returns to its original position. This cycle then repeats itself as long as the switch remains in the on position. Essentially, what we're seeing is a rapid, continuous process of magnetization, movement, sound production, and demagnetization, forming the basis of how many electric bell mechanisms work efficiently and reliably. It's a clever use of simple electrical and magnetic principles to create a repeating sound signal.